All right, everybody. So we are going to start with stoichiometry today. Big, scary chemistry word that you maybe heard of before you started this class. It can be intimidating. You think you think, oh my goodness, what does this mean? And how do I say it? How do I spell it? Um, and it can be a more challenging thing. It's really just math ratios is what we're looking at. So things that you've gotten introduced to with factor labeling, now we're taking it a step further. So this is in your notes. I think around page 12 or 13, I believe, is where you're going to see it. Yep, page 13 in your guided notes after the molecular formula information. And so stoichiometry, what is this? It's a branch of chemistry that studies the amounts of reactants used up during a reaction and then how much product should be produced. So why is stoichiometry important in our world? To an engineer, a chemical engineer, or a chemical plant, it's quite important for them. Why? Well, it allows for chemical plants and mass producers to ensure that their more expensive reagent, which we're going to learn is called the limiting reagent, is completely used up by adding too much of the cheaper reagent. So those are the big reasons as to why chemical engineers and plant operators in a chemical plant are paying attention to the mathematics of a chemical reaction. They want to keep the boss happy and use up all of the expensive reagent and make sure to have a lot of that cheaper one left over. So, what else? For a chemical engineer, this is the profession that helps them to do these things. So I'm going to try to show this video. Hopefully it works and that you guys can actually hear it.
An engineer is a person that solves problems.
And a chemical engineer is somebody who knows enough mechanics to confuse a chemist, enough chemistry to confuse a mechanic, and enough math to confuse himself.
People come to us with ideas, innovations, new technology, and they want to scale it up. They want to take it from something that's a beaker size and make it bigger, and we do it in an economically viable way. We had a client come to us, and they wanted to attempt to make textiles out of stinging nettle, which is a weed. So we took the material that they sent us, and we put it through our small-scale processing system, pulped it, and then we put it through an extruder to extrude it into a fiber. And that fiber can be woven into textiles.
The fibers that they're making with stinging nettle now are rayon-like fibers, which come from renewable feedstocks versus polyester, which are petroleum-based. So taking a renewable feedstock and offsetting a petroleum-based feedstock is better for the environment.
So waste can actually be valuable instead of being detrimental to the environment.
There is no such thing as waste. Whenever you're taking something and you're making something else, you're going to be doing an impact to the environment. You just want to make sure you minimize that wherever possible. And it's the responsibility really of chemical engineers to make sure that that impact is minimized. I think at one point engineering actually used to be something that you became. Right now I think engineering is a lot more evolved into a skill set or a way of thinking that allows who you are to actually benefit the world by solving problems, by doing interesting things.
Hi, I'm Laura.
And I'm Wade.
And we're chemical engineers.
Okay, hopefully that worked. It's always fun to highlight things you could do if you have an interest in chemistry. You don't have to think you have to be anything medicine, that there's a lot of other opportunities out there. Okay, so the types of problems we're going to learn how to solve, and we're only going to be working with number 1 today. We're going to slowly get through all of these, but we'll be looking at mole-to-mole conversions, which is determining how many moles of a product are made from a given number of moles of a reactant, and then also vice versa. We're going to learn how to go from mole to mass, which is determining how many grams of a product are made from a given number of moles of a reactant, and then vice versa. And then we're going to learn how to go mass to mass, which is determining how many grams of a product are made from a given amount of grams of a reactant. Okay, so we'll get there. Not done yet. So we're going to do number 1 today. Ms. Merkus is going to do a video of showing you how to do numbers 2 and 3 in our next class. And then the third day that we do a lecture on stoichiometry, we'll address these last two, which is moles to particles and then mass to particles. So in moles to particles, we determine how many moles of a product are made from a given amount of particles of a reactant, and then mass to particles, determining how many grams of a product are made from a given amount of particles of a reactant, and vice versa. Okay. We also, after we understand this is going to carry us, remember this unit's going to carry us all the way through Christmas time and your break right before Christmas. So the last piece of this is something that's called limiting and excess reagents. So once we learn the basic mechanics of how to do molar conversions, we're going to put in the idea of what chemical engineers do, of thinking limiting and excess, and what factory plants have to work with if they're making maybe laundry detergent, and all the things that go into making laundry detergents, and the reactions that might happen, or if they're etching metals or glasses or whatever it might be. This becomes very important for them in their work. So we're going to learn how to do this in a micro scale, okay, in a lab, and then factories apply what we learn in the micro and apply it to their big factory chains and the lines that they're making. So what are we looking at here? Okay, limiting and excess reagents. We're going to be determining which of the two or more, but a lot of times it's just 2 reactants will be used up first, and then using that calculation to predict how much product is made. Okay, a lot like a recipe. When you think if you're making cookies, you might be limited by the amount of flour you have, or you might be limited by the chocolate chips that you have, or whatever it might be. And then using our knowledge of limiting and excess reagents, we will learn how to compare what's called the theoretical yield with the actual yield, and then determine what is considered to be the percent yield in a lab setting. Okay, so that gives you an overview of everything we'll be doing with stoichiometry. Again, we're just going to address that letter I, mole to mole type of calculation today in today's lesson. If you look at this graphic on the next page, that gives you, and what's actually in your notes is a little more than what you see here. It gives you an idea of how we can convert, how we can move across a reaction. And I might do this with some live warm-ups with you guys of how we can use this. But here's the basic idea. We have to start with a balanced equation. If we don't write a balanced equation, we're not going to do, and we got to have the right chemical formulas, right? So we won't be able to do anything if our equation's not balanced. Then we want to determine what is it we're trying to find. Okay, so we have to really dissect the units that are in the problem and understand, grams is going to go with mass, and what will particle count look like, what will moles finish off as. So we have to understand what we're trying to find, and we have to determine what it is that we're given. Okay, so from what we're given to what we find. And then we're going to use dimensional analysis, which sometimes we call it the train track method, that you have been getting used to with some of those molar conversions that we've already done to solve the problem. Okay, so we're going to start with looking at mole ratios today. Now, you're going to be doing this as homework. I'm just going to continue with the lecture, but you're going to see a mole ratio section in your actual packet of information. So even though this is written as it is, realize you're going to be doing this as homework. So using the coefficients in a balanced reaction, take a minute to complete the mole ratio worksheet. Now, your choice if you want to hit pause and do it now, or if you'd like to watch all of the video. But that's really the first page, maybe the first 2 pages of your practice packet. And then you could, after you try that and complete it, you could try to come back to this video and continue watching. Or like I said, I'm about to go through it as well. You can listen to the rest of this video and then attack all of your homework. So your choice on how you maybe want to do this. Okay, but if we were in class, I would probably force you to think it out a little bit with a partner next to you, and before we actually did some note taking. Okay, so if we're going from moles of a reactant to moles of a product, or it could be moles of a product to moles of a reactant, we call those mole to mole stoichiometric problems. So it's going to be the easiest, the simplest steps. That most of the time, these are one-step problems that we do. And we're going to use this example. And I'm going to have to go back and forth between projecting my whiteboard and then coming back to this problem. But take a moment, and I want you to push pause in between, and I want you to write the balanced equation. So propane, now on this slide, you go, well, what's propane? But if you actually look on page 14 of your notes, we told you in the notes that propane is C3H8. So propane is going to react with excess oxygen gas. So you got to think back, and this is what stoichiometry makes you do. The chemical reaction unit, you've got to go all the way back to that and think, okay, what are the products? Whenever something like a hydrocarbon is reacting with oxygen, what are the products? So pause for a moment, predict products, balance the equation, and then come back here and we'll take a look at your answer, and we're going to kind of move on from that, okay? Okay, so hopefully you attempted to, excuse my hand, to do, and you're going to, I'm sorry that we got a little bit of a shadow. I don't know if I'm going to be able to fix that. I could try possibly. See what I can come up with here. I don't know if this is going to make it worse. Well, we'll just deal. Okay, so C3H8O2, this is a combustion. So we end up with CO2 and H2O. So whenever you balance, hopefully you put a 3 here. We look at our hydrogens, we need a 4 here. And then we end up needing, so 6 plus 4, we have 10 oxygens. So we'd put a 5 here in front of oxygen. If we, like I said, I'm going to have to be going back and forth between these. Let's see if I can do this without irritating you staring at my hand all the time. But what we're looking at now is this question right here. And on your handout, it goes with, on the bottom of page 14, you can see it, and I might just end up going back and forth with that so we don't have to keep monkeying back and forth here. But I'm looking right now at this problem. So how many moles of carbon dioxide are produced? Okay, so just some heads up, how would I maybe use this schematic here? This is where we begin. You know, the problem up above in the bolded words says we have 2.0 moles of methane. So that's how I use this is, you know, that's what I'm given, 2.0 moles of methane. What am I trying to find out? Well, the question says in this, and here we get to the question, how many moles of carbon dioxide are produced? So I'm trying to figure out how many moles of CO2 am I going to get? So I can use this graphic to do that same idea. I have 2.0 moles of methane. Sorry, I don't know why I'm saying methane, propane. And I'm trying to find this right here. You know, how many moles of carbon dioxide? That really is just one arrow, even though it's an arrow that's got, you know, a little bit of a crookedness to it. That's just one step, just one arrow of what I need to do. And I can always go moles to moles. So, you know, this eventually we're going to learn how to go from mass to moles, from mass to moles to moles to mass. We're going to eventually put particles in here, but we're starting with the very simplest step of just going mole to mole. Okay, so how do I set that up? And you could just do this problem, at the bottom of this page here, I think would be a good place for it. So we would say something like this. The question was, how many moles of CO2 am I going to get? And the beginning problem said we had a starting amount of 2.0 moles of propane, of C3H8. Okay? So remember what you've learned before with molar conversions. I have no choice. This has to come down here as far as the unit. Mole of C3H8. I can always go moles to moles. So just like we saw with that graphic, you can always go moles to moles. What do we go to? Well, moles of what we're looking for, CO2. Now, if you were in my class, one of the things I said before when we were doing molar conversions, I said, you guys, anytime you see mole, write the number 1 for now. Just put the number 1 by it when you're using it with molar conversions. I said, but there's going to be a point where you can't do that anymore. All right, we've reached that point. So we're now at a spot where we might sometimes put a 1, but we might sometimes put something besides that. So how am I going to know what to put? Now when we do stoichiometry, we are always going to, for looking at moles for us, for stoichiometry, equals looking at the coefficients. Okay, so we don't write how many coefficients, but you have to know for this that mole equals coefficients. That's how I find it. All right, remember what's invisible right here? It's an invisible number 1. We're going to need to know that. So the reason I put a 1 here now is not because Linsky said always do a number 1. That was with molar conversions. The reason I do this now is moles equal coefficients when I do stoichiometry. So I put a 1 here, and then what do I put for carbon dioxide? A 3. Why do I know that? I find the match. CO2, CO2, put a 3, put a 3. Okay, so then these cancel. I'm left on the right-hand side with mole of CO2, and that's exactly what I'm allowed to be left with. That's what I want to get to. So I stop when my left and my right units equal. So mathematically, what am I doing? 2.0 times 3, and I end up with 6.0 moles of CO2. Okay, let's turn the paper over and try the next problem. And I can't show you the handout because, I shouldn't have erased all of the equation. Shoot, let me rewrite the equation because we're still looking at the same thing, the same reaction. C3H8 plus oxygen to give us CO2 and H2O. That's still happening. We had a 3 here, a 4 here, and a 5 there, I believe. Okay. So that part's the same. It's just now we have another question, and we could ask, well, how many moles of water did we end up with? So remember from the problem before, we haven't changed anything. We still have a starting amount of 2.0 moles of propane. So we have this. Just to understand, where we're at. And we're being asked now, how many moles of water? Okay, so that's what we're trying to do. If I have coefficients, I can make this adjustment. All right, so how do I set this up using molar and dimensional analysis? I'm asked how many moles of water am I going to get with 2.0 moles of C3H8? Okay, I have no choice. This unit always goes bottom right. Top left goes down to bottom right. Mole of C3H8. If you're a methodical thinker, you're going to have no problem with this. So just, even if you're going, I'm not quite getting this, practice the method and you'll eventually catch the why behind. So practice the method, you're going to catch the why behind this. So I go mole of C3H8. How do I know what to put on the top? Always look to where you're going. I have no interest this time in carbon dioxide or oxygen or anything. My interest is in mole of water. So if I know a relationship between mole of propane and mole of water, that's where I want to go. And we always know a relationship of mole to mole. How do we always know a relationship? What did I tell you in the unit or in the problem before? For stoichiometry, mole is code word for coefficient. We always know coefficients of all of these things if we have a balanced equation. So I can absolutely always make this connection. Where do I find these numbers? They're the coefficient. What's invisible here? The number 1. That's why I put a 1 here. Now I look for water and I match. Number 4 here. Mole of propane cancels. And what am I doing mathematically? 2.0 times 4 divided by 1. 8.0 moles of water. Okay, with problem 2, I want you to first just write the balanced equation. So push pause, take time to write it on your own. This is good practice for nomenclature. You're going to see that again in the semester final and also at the end of the year test. So practice just writing it, practice balancing it, and then push play again, and let's do some comparison here. Okay, so hopefully you ended up with something that looked like this. So sodium carbonate would be Na2CO3. You should have gotten that it reacts with 2 hydrochloric acids to give you 2 sodium chlorides plus water plus carbon dioxide. And all of those are a 1-to-1. All right, they told us, and I sometimes like to write this underneath the problem so I know where it is that I'm going. So they told us we have 3.2 moles of sodium carbonate. Tells me we got tons of, so I'm going to start using this word like excess, that we react with excess hydrochloric, meaning that there's so much hydrochloric there, I don't have to wonder, oh my goodness, did we have enough? There's tons of hydrochloric. And then we end up with, in their question, how many moles of water are produced? So here's my question mark. Looking for how many moles of water. I'm going to take that and turn it into my dimensional analysis. And this is where you have to write, just write small, and you have to write in the chemical formulas. Okay, so don't get lazy and just write how many moles. You're going to get lost because now I'm going between a reaction. So stoichiometry is different from molar conversions because now I'm involving a chemical reaction. Everything you've done before stayed with one substance. Now we're looking at a chemical reaction and we're going from one substance in a reaction to another substance. Okay, so how many moles of water am I going to end up with if I get to react fully 3.2 moles of sodium carbonate? Okay, think of the rules. Get methodical. Excuse me. I have to put mole of sodium carbonate down here. I have no choice. Okay, remember what I've told you. Mole in stoichiometry equals coefficient. It's code word. So these things equal each other. That's the equal sign. All right. Well, if that's the case, I always know a relationship between code word coefficient in front of sodium carbonate and code word coefficient in front of water. I always know that as long as I have a balanced equation. So mole of sodium carbonate, well, what am I going to put up here? Mole of water. That's code word for coefficient. That's easy. I've been doing that since the last unit and been rocking it, right? Okay, no longer do we just get to stick the number 1 in there. We only put the number 1 if that's what code word coefficient has in front of it. All right, so let's take a look. I look at mole, code word coefficient. What's the coefficient in front of sodium carbonate? It's a 1 this time. So I put this here. Coefficient. So code word mole, coefficient. What's the coefficient in front of water this time? It's also a 1. Wow, this is boring. But we had to do that to make sure that we end up with the right answer. What am I doing mathematically? Easy stuff. 3.2 times 1. Okay, nothing special. So we end up with 3.2 moles of water. Okay, how about you just push pause and try that last one on your own. I'm going to do it obviously as well, but see how you do. See if you're getting it. This is the last one we're going to go through before you try to do your own homework, and we'll come back to it and do a comparison. Okay, so I'm sticking with this same equation, right? But now I'm just asking for a different product. So let me do a little bit of cleanup here. We don't want to lose the equation like I did last time and I got overzealous. Okay, remember there's that just invisible number 1 right here. Might as well use it. There's also a 1 in front of water and carbon dioxide, but I wrote so scrunched together. Might make a mess if I try and fix that. Okay, so we still are told at the very beginning of this problem we have 3.2 moles of sodium carbonate, but this time that question says, well, how many moles of sodium chloride do we get? So this is where I'm going to put, this will be what I put on the left-hand side of the equal sign, my question mark. So how many mole of, I'm going to write the substance so I don't get confused. So sodium chloride will I get from 3.2 mole of Na2CO3. Okay, what do? Methodical. Top left goes to bottom right. If we keep having to do more steps, and we will, it's always the same. Top left unit goes to the bottom right. Not the number. Leave the number alone. Illegal. Don't touch it. Just the unit. Okay, so mole, I'm going to just write it like this because I wrote too big. All right. What do I put on the top? Well, if I can, I'm going to put mole of NaCl. And remember the code word, mole equals coefficient. Do I know a relationship? So I'm allowed to do this if I know a relationship between mole of sodium carbonate and mole of sodium chloride. If I understand that mole means code word for coefficient, I always know the coefficients that go in front of sodium carbonate and the coefficient that goes in front of sodium chloride. Why? Because I wrote a balanced equation. So I can totally do this. Mole of NaCl. All right, what number? So I always, if you notice, you guys, I always do the unit first, and I look at the number once I get my units figured out. Like I don't try to do it all at once. Like I just go, okay, what do I got to get to? Mole of sodium carbonate to mole of sodium chloride. Then I go back and look at the numbers. Okay, I always do my units first, then look at the numbers. That's how it works in my brain. Doesn't mean it works that way in your brain, but I like to kind of split it up like that. Okay, code word coefficient. A 1 here, a 2 here. And I know I'm done when these will always cancel out, top and bottom, and I'm left with what's on the left-hand side, same unit as on the right. And now I'm just mathematically 3.2 times 2, divide that whole thing by 1. Okay, what does that really mean? 6.4. Moles of what? Moles of NaCl. Okay, so starting off with the simplest today, we're going to learn how to pull mass into it on Monday, and then we're going to learn how to pull particle count into it on Tuesday. All right, so we break up stoichiometry into 3 separate days of lessons. Hang in there. You're going to see your homework that is part of this. And if you have any questions, then reach out to Miss Merkus or I.